Review problem number 7. We've got a roller coaster and we're given the initial height and the initial speed, which is 0, and we want to find the speed at some other points along that roller coaster track. Right, so here we are at the beginning of the ride. At point A, and then we'll end up at points B and C. And this is one of those problems that is pretty simple to solve using conservation of energy. It would be extremely difficult to solve using Newton's laws of kinematics because there's this crazy curved path. And if you tried to solve it using Newton's second law, you'd end up having to solve for the acceleration at each of the points along this path. You'd have to know the slope of the track at each of those points. It would be described by some really complicated equation. And that would all be really tough to do. Would require a lot of calculus and probably numerical calculations that you need a computer to do for you. But when we use conservation of energy, we can bypass all that complexity because all we need to know is information about some initial point and information about some final point. And that gives us the equation we need to solve the problem. So we're ignoring any friction or air resistance. We're ignoring non-conservative forces in this problem. So the work by any non-conservative forces equals 0, which means that initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy for any initial and final points. So let's just fill this in. mgy initial plus 1/2 mv initial squared mgy final plus 1/2 mv final squared. The mass is irrelevant. It crosses out of all of these things. So we can solve this equation. Try this algebra out at home if you like. V initial squared plus 2g y initial minus y final. That's true for any 2 points on the track. So to answer these questions, what's the speed at point B? What's the speed at point C? All you need to do is substitute your values for point A for initial and your values for point B for final. And similarly for point C. So this is really the master equation that'll allow you to solve for the speed at any point along this track. Keep in mind that the speed at point A, if you're using V initial at point A, that's 0, so this first thing will go away. So that's all you got to do. Kind of works like magic. And so that was kind of the first part of the problem. The second part of the problem is it asks for the amount of work done by the gravity force. And again, this notation, sorry we only have 26 letters in the English alphabet. The W here is referring to the work done by gravity, not to the gravitational force itself. So this work done by gravity equals the change in kinetic energy or minus the change in potential energy. That's the Work-Energy Theorem. So whichever way you want to calculate it, you can do that. So for instance, the work done by gravity as you go from point A to point C would equal the change in kinetic energy from point A to point C, or KE at point C minus KE at point A. Or if you wanted to calculate it with the potential energies, it would be the potential energy at A minus the potential energy at C. That's minus the change in potential energy. The negative sign flips the order of those. And you can do the same process for finding the work done from point A to point B, or from point B to point C, or any possible combination. So a problem like this, I might change it up a little bit on the exam by asking you to explain why conservation of energy for this problem is so much easier than using Newton's laws. And as I mentioned earlier, it's because all you need to know is the starting point and ending point, and you don't need to know any of the complicated details about the path taken to get from start to end. That's because gravity is a conservative force. And I might ask you some other questions, like to find speeds at some different points along the track, or might change the shape of the track, but the shape of the track doesn't matter, just the heights of where you're at. Okay, that's review problem number 7.